In this video, we're going to look at heating curves, or what the IB likes to call phase change curves. We're also going to introduce specific heat capacity, and latent heat. Without going into any details, if we wanted to produce a heating curve, we'd do something like this. We'd get a sample of a solid substance, and then we're going to add heat to it. But we're going to add that heat at a constant rate. We're going to have a sensor, that's a thermometer, and it's going to measure the temperature of our substance. And of course, what's going to happen is that we add heat, and then eventually our substance begins to melt, and we're going to end up with a liquid. And then we continue to add heat at a constant rate, and that liquid warms up, and eventually it begins to boil, and eventually you're going to end up with a gas. In a heating curve, you just plot the temperature against the amount of heat that you've added to your substance. So here's our general heating curve. We've got on the vertical axis the temperature, and we've got heat, or Q, on the horizontal axis. And in this particular case, we're adding heat to 1 gram of water, 1 gram of H2O. All the heating curves have this same basic shape. It starts out as a solid, and then as you add heat at a constant rate, the temperature goes up at a constant rate. And eventually you reach the melting point. So at this point here, you've got nothing but solid, but it's beginning to melt. Then you keep adding heat, and it all melts. And it's kind of surprising that the temperature doesn't change until it's all melted. So at this point here, you've got all liquid. Then the temperature will begin to rise. So you add heat, and the temperature will rise at a constant rate, warming up that liquid until it begins to boil. And this is the point where it begins to boil. It's still a liquid at that point. You continue to add heat, and you boil away more and more of the liquid, creating more and more gas, and eventually you get nothing but gas. But until you get nothing but gas, there's no change in temperature. It stays at 100 degrees Celsius. So what's the temperature of boiling water? Well, it's always 100 degrees Celsius. Once you've got nothing but gas, if you trap it, you can continue to add heat and increase its temperature. So those are the basic features of a heating curve. So at this point, you might be asking yourself, why do we get these temperature plateaus? I've done experiments with heating curves with students, and some of them absolutely do not believe when there's a temperature plateau. They're adding heat, and the temperature is not going up, and they don't understand it. So let's make sure that you do understand it. You'll recall from the last video that I had a little model. So we've got two molecules in a solid. We said that there was electrostatic forces between them, and we represented those forces by springs. And then we said there was a slider in between the springs, and it would slide on a rod, but in the solid case there was a little bit of glue holding that slider on there so that it wouldn't move. So what happens is we add heat. So we add Q. Of course, this increases the vibrations, which is really just an increase in the kinetic energy of the molecules. And we know that temperature is a measure of the average kinetic energy per molecule. So if we're increasing kinetic energy, that means we're increasing temperature. So you want to make a strong association here between kinetic energy and temperature. Now, of course, you'd also be increasing the potential energy a bit because the molecules would get a little bit farther apart. Now, eventually, you're going to reach the melting temperature. And what happens at the melting temperature is that the kinetic energy of these molecules is just at the threshold point where you begin to break the glue. So every time you try to increase the temperature, you just end up breaking the glue. And of course, when the glue is broken, the slider can move, and there's an extra degree of freedom. And it's that extra degree of freedom that makes a liquid different from a solid. So at the melting temperature, the bonds are at the threshold of changing from solid to liquid. And any additional heat energy only changes the bonding, the potential energy. The kinetic energy, and therefore the temperature, remains constant. Okay, I have two questions for you here. I'd like you to look at the heating curve very carefully and see if you can answer them. So pause the video, try the questions, come back for the answer. In the first question, we're just asking, well, how much heat do we have to add in order to raise the temperature by 1 degree? And in this case, we're talking about water, so we're talking about in the liquid form. We're talking about this section of our heating curve. Now, it takes 100 calories to raise by 100 degrees. This is a linear relationship, so it should take just 1 calorie to raise the temperature of water by 1 degree. So hopefully you said it takes 1 calorie to raise 1 gram of water by 1 degree Celsius. You know, remember the heating curve was for 1 gram of water. Second question, how much energy would be required to heat up 2 grams of liquid water from 0 to 100 degrees? So now, of course, we've got twice as much mass, twice as much stuff to heat up. So that would contribute a factor of 2. And instead of heating it up by 1 degree, we're going to heat it up by 100 degrees. And that should introduce a factor of 100. So instead of only using 1 calorie, it should take 2 times 100 times 1 calorie. So it would take 200 calories to heat up 2 grams of water from 0 to 100 degrees. So we just said that it takes 1 calorie of heat energy to raise the temperature of 1 gram of water by 1 degree Celsius. And this is really the specific heat capacity of water. If we were to generally define specific heat capacity for any substance, we would say that it's the amount of heat energy needed to raise a unit mass of the substance by 1 degree. That could be 1 degree Celsius or 1 Kelvin. So this here is our definition of specific heat capacity. And generally, we use a small letter c to represent the specific heat capacity, and it's generally going to be equal to the amount of heat added divided by the mass of the substance divided by the change in temperature. So to see how that works, in our first example for C of water, we had that it took 1 calorie to raise 1 gram by 1 degree Celsius. So we get an answer there for the specific heat capacity of water of 1. In our second example, we used 200 calories to raise 2 grams by 100 degrees Celsius. So we end up with that same basic ratio, the same value for the specific heat capacity of water, 1 calorie per gram degrees Celsius. So we've been talking about specific heat capacity. So we talk about the specific heat capacity for substances, such as iron, or water, or gold, etc. But there's something else that's closely related that's simply called the heat capacity. And it's about objects, such as a hammer. But it could be a piano, or it could be a boiler with water in it. It could be any object. And we use a capital C for this heat capacity, whereas for the specific heat capacity, we use a small c. And when we defined the specific heat capacity, we said it was the heat energy needed to raise 1 gram of a substance by 1 degree Celsius. And when we defined heat capacity, it's defined in a very similar manner. We say it's the heat energy needed to raise an object. We don't have to specify the mass of the object. Whatever the object is, it will take a certain amount of energy to raise that object by 1 degree Celsius. So if our equation for specific heat capacity is the heat added, divide by the mass to make it per unit mass, divide by the temperature to make it per 1 degree temperature change, then our equation for the heat capacity, the big C, is just the amount of heat needed acting on that object, whatever its mass is, to raise its temperature by 1 degree. Let's take a look at a couple very typical examples of how we'd use our specific heat capacity equations. And typically, you look up the specific heat capacities of different substances in tables, such as the one here to the left. So pause the video, try the question, come back for the answer. So let's start with our equation for specific heat capacity. It's equal to the heat added per unit mass per degree change in temperature. Now, we're looking for the increase in temperature, so why don't we rearrange that right now. The change in temperature is going to equal Q divided by MC. The heat added, well, we've got 500 joules of heat being added. Our mass is some 200 grams. Now, be careful about the units because we're dealing with joules and grams here. When we look at our table for lead, we get a value here in joules per kilogram. It's 130 joules per kilogram. Of course, it's going to take a lot less energy to raise just a gram by 1 degree Celsius. In fact, you can just divide by 1,000. This is going to be 0.130 joules per gram degrees Celsius. So let's substitute that in times 0.130 joules per gram degrees Celsius. Work that out and you should get a change in temperature of about 19 degrees Celsius. Here's a question that involves the relationship between heat capacity and specific heat capacity. Pause the video, read the question, try it out, come back for the answer. So just writing down my equations, the big heat capacity is going to be Q all over delta T, whereas the specific heat capacity is going to be Q all over M delta T. And if I do something very simple here and simply multiply both sides of the specific heat capacity equation by mass, you'll see that I get Q over delta T on the right hand side here, which is simply big C. In other words, M times little c is equal to big C. So what we need to do here, we want to find out big C for this hammer. And the hammer has two parts. So we'll have to add up the heat capacity for the head of the hammer plus the heat capacity for the shaft of the hammer. For the head of the hammer, we've got a mass of 500 grams, and it's made of iron. Iron has a specific heat capacity of 0.11 calories per gram degrees Celsius. And then for the heat capacity of the shaft, it's going to be made out of wood. It's 200 grams, and the specific heat capacity of wood is 0.4. That would be in calories per gram degrees Celsius. So I'm going to get here 55 calories per degree Celsius plus another 80 calories per degree Celsius. So it's going to take a total of 135 calories to raise the hammer shaft plus head by 1 degree. Okay, let's come back to our heating curve. Using the heating curve, how many calories are needed to change 1 gram of 0 degree ice to water? Pause the video, try that question. Well, here's ice at 0 degrees, and here's the ice all melted into water, also at 0 degrees. And you can see it takes 80 calories to melt 1 gram of ice. So we just said it takes 80 calories to melt 1 gram of water. And we have something that's called the latent heat of fusion. And it would be defined this way. It's the heat energy needed to melt 1 gram of a substance. And we give it the symbol L with a subscript F for fusion. So for water, the latent heat of fusion is equal to 80 calories per gram. We also have something called the latent heat of vaporization. And we give it the symbol capital L with a subscript V for vaporization. And you can probably guess what its definition is. It's the heat energy needed to vaporize 1 gram of a substance. And for H2O, the value of the latent heat of vaporization is 540 calories per gram. And once again, we can see that on our heating curve. And it's this energy here. It's the energy to take water at 100 degrees Celsius and turn it into nothing but steam, still at 100 degrees Celsius. Let's try a problem involving latent heats. So you're going to need to use the table, read over the question, try the problem, come back for the answer. So the first thing is that, well, whenever we're dealing with latent heats, we're dealing with those temperature plateaus. So you want to do it at a constant temperature equal to the melting temperature, and for lead, that's 327 degrees Celsius. So this is melting. We need latent heat of fusion for iron, and it should be equal to the heat added divided by the mass. Of course, if we rearrange that, we'll get that the heat added is going to have to equal the mass times the latent heat. And we've got a 500 gram sample. And now let's look for the latent heat of iron. That's going to be, well, 5.9 kilocalories per kilogram. Well, that's exactly the same as a calorie per gram. So this is the same as writing 5.9 calories per gram. So now we've got our masses in the same unit, and I can multiply that out, and I'll get approximately 3,000 calories. So it's going to take 3,000 calories to melt that 500 grams of lead. Here's an IB problem that was not particularly well done. Pause the video, read it over, try it out for yourself, come back for the answer. The first thing we probably want to notice about this problem is that we know the specific heat capacity of water. That means we know the C value in this region. It's 4,200. But we don't know the L value in this region where the ice is melting, and we don't know the C value here for ice when the ice is being warmed up. So we don't have those values. We have a little more information in this region here. So when we're asked for the rate at which energy is supplied to the ice, we want to use the information from this region. It's the same rate all the way through, but we've got extra information that we can use in this region here. So the heat added in that region would be given by Q equals M times the specific heat capacity of water times the change in temperature in that region. Q here is the heat energy that's been added. And you'll recall that power is equal to the change in energy over time. So the type of energy that we're talking about here is heat energy. So we can say that that change in energy, the heat energy, must equal power times time. And the power we're talking about is this power that we're trying to prove is 530 watts. M is, of course, 0.25 kilograms. C is 4,200 joules per kilogram degree Celsius, just SI units. And our change in temperature, well, it starts out at 0 degrees here, and it rises to 15 degrees here. So it's a 15 degree change in temperature. So all we need now is the time here. So our time started right here at 165 seconds, and finishes off right here at 195 seconds. So there's a 30-second time interval over which the water warms up. So we've got that power times 30 must equal 0.25 times 4200 times 15. And if you work that out, you should get 525 watts, or 525 joules per second. And then going to two significant digits, that would be 530 watts. So there's part I. Next, we're asked for the specific heat capacity of the ice. Well, we'll use this region here where we're warming up the ice. And once again, we can say that Q will equal mc delta T. But now we know the power. Let's once again write that heat added in terms of power. Power times time must be equal to mc delta T. Power is going to be 530. The time, we're going to start at 0 seconds and go to right here, which is what, 15 seconds of time. We heat up the ice for 15 seconds. It's that 0.25 kilograms specific heat capacity of ice. Well, that's what we're looking for. And the change in temperature, we start at minus 20, we go up to 0, so we've got a change of 20 degrees there. So now we can solve for this C, the specific heat capacity of ice. Should get 1590 joules per kilogram degrees Celsius, which is 1600 joules per kilogram degrees Celsius to two significant digits. And the last part of the question asks for the latent heat of fusion of ice. So we're interested in that flat region of the curve, which extends from 15 seconds to 165 seconds. So once again, we can write Q equals ml, and we can write that heat added as power times time. We're going to solve for this L, the latent heat of fusion of ice. So it's going to equal power times time over mass. Our power, once again, is 530 watts. The amount of time, 165 minus 15 would be 150 seconds. And we've got to divide that by the mass of 0.25 kilograms. Work that out and you should get about 318,000 joules per kilogram, or going to two significant digits, 320,000. In this question, we're asked how much heat energy is required to take 3 grams of ice at -8 degrees Celsius and turn it into steam at 120 degrees Celsius. Starting here as ice is at -8 degrees Celsius, and we warm up that ice to 0, then we melt it, then we have to take that water and warm it up to 100 degrees so it'll start boiling. We have to boil away all the water, and then we have to warm up the steam until we get to 120 degrees. Now, we could use the graph to do this problem, except that we don't have any graphical values in this region or in this region. Let's make a little estimate. What we're going to do is just calculate from the graph how much energy it would take to go from here, I'll call that point 1, to here, which I'll call point 2. So we're just going to ignore those little regions at the beginning and the end. If we do that, the total energy is going to be that 80 calories to melt 1 gram of ice, plus 100 calories to warm up 1 gram of water to 100 degrees, plus another 540 calories to boil away 1 gram of water. Now, of course, we don't have 1 gram of water. We actually have 3 grams of water. So these values are really calories per gram. And we're going to multiply that by 3 grams to get the total number of calories needed to go from point 1 to point 2. And if you do the calculation there, you get 2,160 calories. Graphs are kind of awkward. They're difficult to carry around. They're not all that accurate. So we'd rather do this more mathematically. Let's see how we do it more mathematically. And we should end up with an answer that's a little bit bigger than 2,160 calories. So the way we'd normally do this problem is we're looking for Q total. And we're going to have to sum up the heat needed to warm the ice plus the heat needed to to melt the ice, plus the heat needed to warm that melted ice, plus the heat needed to boil, and plus the heat needed to warm the steam. And we have these two definitions. We have specific heat capacity, the heat added per unit mass, degree temperature change, and the latent heat, the heat added per unit mass. If I rearrange those, I get Q equals mc delta T, and Q equals ml. So in these three terms here, where I'm warming, I'm going to use one of these mc delta T terms. Whereas in these two terms where I'm changing phase, melting or boiling, I'm going to use an ml. For boiling, that's the latent heat of vaporization. For melting, that's the latent heat of fusion. So our mass here is 3 grams. So I'm going to put a 3 in for all these terms. The C here, that's really for ice. And we can look that up. It's 0.5 in calories per gram. And it's going to change its temperature from -8 degrees up to 0. So it's going to raise its temperature by 8 degrees here. So that's the energy needed to warm the ice from 8 to 0. Then we need the latent heat of fusion of water, and it turns out to be 80 calories per gram. So I'm going to multiply by 80 here. This here is to warm water. So the C I'm using here, it's not the same as the C here. This is the C for water. And it turns out to be 1. And now we're raising the temperature from 0 degrees to 100. So we're raising it by 100 degrees. Then here, this is where we're boiling away the water. It takes 540 calories per gram to boil water. And then finally, we're going to warm the steam. Turns out steam has the same, or very close to being the same, specific heat capacity as ice, at 0.5. And this time we've got to raise the temperature from 100 to 120, so that's a 20 degree increase in temperature. So these are all energy terms. This first term is going to come out to be 12 calories. Second term, 240 calories. Third term, 300 calories. Next term is very big. It's going to be 3 times 540, or 1,620 calories. And the last term is going to be 30 calories. And so we can see here that the terms at the beginning and the end are quite a bit smaller than the other terms. The biggest amount of energy is required in breaking those liquid bonds and turning the liquid into a gas. And you should get an answer there of about 2,200 calories, going to 2 significant digits. Let's try to summarize the key points. So we started by drawing a heating curve. That was a graph of temperature against the amount of heat added. Could also be time, but there would be 5 distinct regions in that graph. One where you are warming up the solid phase. Then you would melt that solid phase. Then you would warm up the liquid phase. Then you would have a wide region, lots of energy being added here in order to boil away the liquid. And then, of course, you could warm up the steam finally. And this led to definitions for specific heat capacity, and latent heat. And I'll just write down the equations rather than the definitions here. So specific heat capacity, heat added per unit mass per degree change in temperature. Heat capacity would be the heat added to an object to raise its temperature by 1 degree. And then the latent heat, we'd had 1 for fusion, 1 for vaporization, but in both cases it's just the heat added to change the phase of a unit mass. And eventually we kind of tired of doing the heating curves and we started doing things more mathematically. And for these regions 1, 2, and 3 here, where we're warming up the solid, liquid, or the gas, then we could use that the heat added would be equal to m times the specific heat capacity of the solid, liquid, or gas times the change in temperature. And then in these 2 other regions, call them, say, 4 and 5 here, the heat added for those regions would be equal to the mass times the latent heat of fusion or vaporization, depending on which plateau you're talking about. And keep in mind, we get these plateaus, these are temperature plateaus, because the potential energy is changing, the bonding is changing, but the kinetic energy is not changing, so the temperature doesn't change. That is, the heat is going into potential energy, not kinetic energy. So T is constant. And that's all for today, folks. Thank you very much.